Okay, we're going to talk about a word called differentiability. Differentiability at a point means that the derivative exists at a point. So basically it just means that the slope exists at that point. So if f of x is differentiable at some point x equals c, then we say f prime of c exists. Now, differentiability implies continuity. You can only have a slope if the graph has a point there. But just because a function is continuous does not mean it is differentiable. Okay, let's look at two different examples. So if you look at a graph that is not continuous, right? Let's call this point C. At every single point on this graph, there is a slope except at this point. So if a function is not continuous, it is not differentiable everywhere. Another type of example that's not continuous everywhere would be if you have an asymptote. So every single point on the graphs that's shown, these two branches, it has a slope, so it's differentiable. But at the asymptote, there's no point, so there's no slope. So if a function is not continuous, then we can also say it is not differentiable everywhere. Now, there are examples of graphs that are continuous but may not be differentiable. Examples are graphs that have sharp corners, like an absolute value graph. So in this particular case, there is a slope everywhere except right here at that corner. So at a corner, or you could have a graph with what's called a cusp, it is not differentiable at that point. And the reason is the only way that the slope can exist is if you think about what a derivative it is a limit definition. You need to have a derivative from the right hand of the graph and the left hand of the graph, and it should be approaching the same value. But in this particular case, let's say the slope of the right side is 1, the slope of the left side is -1. It's always 1 and -1, so when it approaches this value right there, that's why it creates the corner, because it's not getting closer and closer to some value from the right and the left side. So that's why the slope does not exist. Another type of graph where you can have a slope that does not exist would be if you have a vertical tangent, right? Slope of a vertical tangent is undefined. So you could have continuous graphs that are not necessarily differentiable everywhere. Okay, now let's take a look at one specific example. So let's look at the graph of absolute value of x minus 2. So I know the vertex here is at 2, and on the right side it looks like this, left side. So it's a V-shaped graph. Okay, just from looking at the graph, I do know that it's not differentiable at x equals 2, because we said above at a corner it's not differentiable. But how would we justify using our definition of the derivative? I'm going to use that alternative definition that we learned. Remember, this is our definition of the derivative, one of the definitions, right? This is the definition for f prime of x. That's the definition for the slope. Now, if I look at every single value to the left of 2, and if I approach 2, so here's 2 right here. As I get closer and closer to 2, the slope of this graph on the left side is always -1, right? It's a line. It's always -1. If I look at the right side, so if I approach 2 from the right side of the graph, this slope is always +1. So these, as you approach 2 from the left and the right side, are not approaching the same value. So it's because that these two values are not the same. That's why it is not differentiable at x equals 2, and that's why it creates that corner.